Our entire cosmos and existence are composed of atoms, which serve as the fundamental building blocks of everything we know. The intriguing question arises: how did atoms come into existence, and where did they originate? While our understanding characterizes atoms as extremely tiny entities, the contemplation arises: could the entire universe be analogous to a single atom? Visualize an atom in your mind. An atom is akin to a tiny hub, termed a nucleus, with super-fast electrons zooming around it. Delving into a curious thought, a puzzle emerges. How do these electrons maintain their rapid orbits around the nucleus without slowing down? This question sparked a profound puzzle in the early 20th century, leading to the captivating development of quantum mechanics. Physicists embarked on a mission to unveil the secrets of atoms. The breakthrough in atomic understanding revealed that each atom consists of a nucleus, resembling a central hub with a positive charge and significant mass. Orbiting around this nucleus are minuscule electrons carrying a negative charge. Armed with this foundational insight, scientists endeavored to construct a more intricate model of the atom. Initially drawing inspiration from our solar system, they envisioned a dense nucleus analogous to the Sun, with smaller bits resembling planets orbiting around it. However, this model faced substantial challenges. According to classical physics, charged particles emitting electromagnetic radiation while orbiting would lose energy, spiraling inward and eventually colliding with the nucleus. Additionally, observed radiation emitted by atoms exhibited specific frequencies, diverging from the continuous emission expected from the solar system model. Enter Niels Bohr, a distinguished physicist from Denmark, who emerged as a pioneer in resolving the perplexities surrounding electron behavior in atoms. In 1913, Bohr introduced a groundbreaking concept. Electrons within an atom are not randomly spinning around but are confined to specific quantized distances from the nucleus. Bohr proposed a minimum distance an electron could maintain from the nucleus, beyond which it could not get any closer. Bohr's ideas were not mere conjectures. They were firmly grounded in the earlier work of German physicist Max Planck, who, a decade prior, introduced the concept of quantization of radiation emission. Planck's idea stated that objects could only absorb or release radiation in fixed, distinct amounts determined by a constant value known as Planck's constant. Building upon Planck's work, Bohr applied the concept of quantization specifically to electrons orbiting a nucleus. He asserted that the smallest orbit an electron could have would possess an angular momentum exactly equal to 1 Planck constant. Larger orbits could exhibit multiples of the Planck constant, but fractions like 1.3 or 2.6 were ruled out. Bohr's intricate model laid the groundwork for a more precise understanding of atomic structure, unraveling the mysteries of electron behavior within the microcosm. Achieving a comprehensive grasp of why electrons adopt specific orbits and adhere to well-defined energy levels necessitated the full-fledged development of quantum mechanics. Electrons, akin to other particles constituting matter, exhibit dual characteristics, acting both as particles and waves. While the conventional perception likens an electron to a miniature planet circling a nucleus, an alternative perspective envisions it as a wave encompassing the nucleus. When waves are confined within a delimited space, they adhere to specific regulations, conforming to standing wave patterns that precisely fit the given space. In essence, Bohr's model and the subsequent development of quantum mechanics provided a comprehensive framework for understanding atomic structures and the intricate behaviors of electrons within them. These insights revolutionized our perception of the microscopic world, offering a profound glimpse into the fundamental nature of our universe at its smallest scales. In the realm of quantum mechanics, the nearest orbit an electron occupies is determined by the first standing wave of that electron. Advanced refinements in quantum mechanics have been made, but the core concept remains consistent. An electron faces quantum mechanical limitations preventing it from approaching the nucleus beyond a certain point. This analogy, likening electron behavior to musical harmonies, serves as a bridge to comprehend the intricate interplay between quantum mechanics and the dynamic dance of particles within the microscopic realm. Another perspective, devoid of quantum mechanics, examines the various energies at play. An electron orbiting a nucleus experiences an electric pull toward the nucleus, consistently attempting to get closer. Simultaneously, the electron possesses kinetic energy pushing it away. For a stable atom, these opposing forces are balanced, resulting in the total energy of an electron in orbit, combining kinetic and potential energies being negative. To remove the electron, energy must be added to the atom. This concept draws parallels with planets orbiting the Sun, where adding energy is required to remove a planet from the solar system. Now let's embark on the intriguing journey of the first atom's formation, intricately woven into the fabric of our vast universe. Atoms, the fundamental building blocks of matter, consist of electrons, protons, and neutrons, which harbor even smaller constituents known as quarks. The origins of these particles can be traced back to a monumental event known as the Big Bang, a cosmic narrative guiding us through the universe's inception. The Big Bang theory suggests that a colossal amount of energy condensed at the universe's birth, leading to the formation of atoms. However, the precise moment of the universe's commencement remains an enigma, and uncertainties surround whether it truly began at all. The standard model of cosmology allows us to trace time back to the predicted singularity, a moment of infinite density where matter and energy were compressed into an infinitesimally small point. Our scientific journey takes us back to a time close to 1 Planck time, approximately 10 to the power of minus 43 seconds. Beyond this point, uncertainty shrouds our vision, leaving us pondering the events preceding the cosmic blink of an eye. In this quest, a quantum theory of gravity, merging the principles governing gravity and quantum mechanics, unfolds during the Planck epoch at an incredibly minuscule scale. Within the Planck epoch, a tapestry of cosmic dynamics unfolds, suggesting the coalescence of fundamental forces into a singular grand force. To explore the universe's early chapters, we delve into the realm of inflation, an extraordinary expansion occurring from approximately 10 to the power of minus 36 seconds to 10 to the power of minus 33 seconds post-Big Bang. This expansion, faster than the speed of light, catapults the cosmos to a scale comparable to a large orange, erasing information about what existed before it. As we navigate this cosmic timeline, we encounter the Big Bang as an epoch when the early universe pulsated with extreme heat, density, and rapid expansion. Inflation, occurring from 10 to the power of minus 36 to minus 33 seconds, remained shrouded in unknown energy sources, setting the stage for the subsequent evolution of the cosmos. The standard model of cosmology is well understood from about 10 to the power of minus 12 seconds, as the universe's energy levels can be recreated in current particle accelerators. Speculation arises about the events from 10 to the power of minus 33 seconds to minus 12 seconds, where gravity, the strong force, and electromagnetic and weak forces were unified. The origin story of the first elementary particles presents itself as a cosmic enigma, with potential narratives placing their genesis in the energetic maelstrom of the Big Bang or within an inflation field transforming inflaton into elementary particles. This cosmic overture unfolds around the epoch of 10 to the power of minus 11 seconds, marking a pivotal juncture as the temperature takes a plunge, inaugurating the quark epoch. During the quark epoch, the cosmic stage witnesses a dynamic interplay between the fundamental forces of electricity and the weak force, leading to electro-weak symmetry breaking. This intricate cosmic ballet is accompanied by the Higgs field acquiring a non-zero potential, endowing mass to elementary particles outlined by the standard model of particle physics. At this juncture, the foundational components for the eventual formation of atoms fall into place, and the temperature of the burgeoning universe hovers around an astounding 1 quadrillion Kelvin. As the cosmic tapestry unfolds, the universe expands and cools, allowing quarks to coalesce into composite particles. A cosmic alchemy transpires as the temperature gradually descends to approximately 1 trillion Kelvin around 10 to the power of minus 5 seconds, leading to the emergence of protons, neutrons, photons, and electrons. With each sequential drop in temperature, a symphony of particle-antiparticle annihilation ensues, engendering pairs like neutrinos and photons. Subtle asymmetries in this cosmic dance allow an excess of particles over their antiparticles, setting the stage for the complex and intricate formation of the early universe. Cosmic phenomena create a unique environment for certain quarks and electrons to endure, paving the cosmic path for the creation of protons, neutrons, and electrons, the elemental building blocks essential for the formation of the first atoms. This intricate choreography sets the stage for the cosmic narrative to unfold, with particles, forces, and temperatures orchestrating a celestial ballet that shapes the very fabric of our cosmic existence. The cancellation process culminates with the lepton epoch around the 1-second mark, when temperatures drop to about 5 billion Kelvin. During this time, leptons finish the canceling out process, and after this impressive display, most matter particles transform into photons and neutrinos. Due to the disparity between matter and its opposite, a small amount of protons, neutrons, and electrons persist, becoming the basic building blocks for atoms. Approximately a few minutes after the universe's inception, the era of Big Bang nucleosynthesis, BBN, commences with equal numbers of protons and neutrons produced. Free neutrons, inherently unstable, undergo beta decay into protons in about 10 to the power of -5 minutes. While the temperature remains high, the balance between proton and neutron conversion is maintained. However, as the universe cools, more neutron decay becomes common. Free neutrons attempt to combine with other hadrons, creating larger nuclei before breaking down. This process results in the universe being composed of approximately 75% hydrogen nuclei and 25% helium-4 nuclei, with small amounts of deuterium, helium-3, and tiny traces of lithium-9 nuclei. In this cosmic chronicle, a significant chapter unfolds during the photon epoch, a period lasting approximately 380,000 years. During the photon epoch, the cosmic tapestry is woven with predominantly ionized nuclei devoid of companion electrons. The cosmic alchemy required for the formation of stable neutral atoms hinges on the essential interplay between electrons and positively charged nucleons. However, the universe remains ensconced in intense heat, rendering electrons temporary companions to nucleons before the relentless force of their high energy propels them into separation. This persistent separation perpetuates a cosmic cloudiness where photons, bearers of light, engage in continuous interactions with nucleons and electrons, slowing their celestial journey through the vast cosmic expanse. As the cosmic drama unfolds, the photon epoch persists until the universe undergoes a transformative cool-down, reaching a temperature of 3,000 Kelvin. At this cosmic juncture, electrons, now endowed with diminished energy, succumb to the electromagnetic force, forging enduring bonds with nucleons in a process heralded as recombination. This cosmic alchemy heralds the birth of stable neutral atoms, liberating photons from their entanglement amid the cosmic tumult of positive nucleons and negative electrons. Henceforth, these photons embark on an unbridled sojourn through the cosmic canvas. For cosmic spectators situated in the cosmic theater, this luminal journey offers a visual spectacle. In the present day, the inaugural light of the universe, christened the cosmic microwave background, CMB, unfolds in all directions. This luminous emissary captures the moment when the first stable neutral atoms make their cosmic debut, unveiling crucial revelations about the nascent universe and the intricate genesis of atoms. As we navigate these cosmic revelations, an intriguing inquiry surfaces. Do atoms ever truly touch each other? This question delves into the fundamental nature of atomic interactions, inviting us to contemplate the profound mysteries that govern the behavior of these elemental building blocks in the grand tapestry of the cosmos. Atoms are constantly engaged in a dance of interaction, but grasping the intricacy of these interactions requires us to redefine our understanding of interaction. Our conventional comprehension of interaction stems at the microscopic level. Atoms and molecules are in perpetual motion, colliding, twisting, and spinning in a chaotic symphony. Amid this microscopic tumult, a significant revelation emerges. Atoms lack a distinct boundary. At its heart, a cluster of protons and neutrons exists, and electrons exist in a cloud of probability, indicating potential locations they might occupy. The principles of quantum mechanics empower us to calculate these probabilities, revealing that they extend across the vast expanse of the universe. Yet in most observable scenarios, electrons tend to remain in close proximity to the nucleus. Consequently, unless we're engaging in high-energy experiments, delving too deeply into these intricacies isn't a pressing concern. Since atoms don't have a solid surface, in a way there's no physical touch because there's never a direct meeting of surfaces. However, touch also implies a close and influential interaction, and in that sense, atoms are always in contact. Atoms interact because of the electromagnetic force arising from the electric charges of electrons and protons inside them. Technically, this force has an infinite range, but it only becomes important when atoms are close enough. Sometimes atoms repel each other due to the electromagnetic force between their electrons. In that brief moment, it's hard to describe their interaction as anything but touching. Even if it's not instant, it still counts as touching. For example, when we look at the cup on the table at the atomic level, we see that the electrons on the cup's outer edge are pushed away by the electrons on the table's outer edge. Despite the gap between the layers of electrons, which is usually there, the atoms are close enough to significantly affect each other. This is evident from the fact that the cup doesn't fall through the table, and the electromagnetic forces between the atoms counteract gravity's pull on the cup. On the big scale, when we say two objects are touching, it reflects the same interaction on the small scale. Atoms can interact in various ways, and it's not as simple as always being pushed away by the electromagnetic force. When atoms approach each other, there's a force called the van der Waals force, which is part of the electromagnetic force. Surprisingly, this force can create bonds between atoms, leading to the creation of molecules. In a molecule, the atoms are essentially in contact with each other. Interestingly, even the nuclei within atoms have the potential to touch, although it's challenging due to the strong electromagnetic repulsion between the positively charged protons in each nucleus. Quantum mechanics comes into play in this scenario. If two atoms are brought close and held together for a certain period, there's a chance, albeit randomly, that their nuclei can mix. This process is known as nuclear fusion, where two separate atoms merge into a single larger atom. When the atoms involved are lighter than iron, this fusion releases energy. This fundamental process is how stars, including our sun, generate the power that sustains them. Now, let's explore the concept of identical atoms within the same element. Note, two atoms of the same chemical element are usually identical. Firstly, electrons in an atom can be in different states, so two atoms of the same element can be different if their electrons are indifferent. Electromagnetism holds protons and neutrons together within the nucleus, overcoming the electromagnetic repulsion. It operates at very short distances, binding quarks, constituents of protons and neutrons, together to form these particles. Returning to the question of color at the atomic level, in bulk reflection, individual atoms do not exhibit colors due to the small wavelengths of light compared to atomic dimensions. However, in thermal radiation, when substances are heated, the agitated atoms release photons. And although individual atoms don't show discernible color, a congregation of particles creates a colorful display. In gas discharge, when electric current passes through a group of atoms, it induces excitement, leading to the release of photons and the manifestation of various colors specific to each element. This results in a unique emission spectrum for each element. Yet, at the atomic level, conventional perceptions of color don't apply, as atoms are much smaller than the wavelength of light. Addressing the query of why protons within the nucleus don't expel each other, fundamental forces come into play. Electromagnetism, although about 10^37 times weaker than the strong nuclear force, is responsible for attracting electrons to protons in atoms. Despite Coulomb's law predicting repulsion between protons in a helium atom, the strong nuclear force, roughly 100 times stronger than electromagnetism, prevails within the nucleus, keeping protons and neutrons bound together. It's crucial to understand that atoms of the same type may possess different numbers of neutrons, giving rise to isotopes. Isotopes have implications, particularly in nuclear reactions and processes like radioactive decay, where different isotopes exhibit distinct characteristics. While isotopes don't impact an atom's chemical reactions, they significantly influence behavior in nuclear reactions. As we explore the concept of identical atoms within the same element, it's highlighted that achieving perfect identicality between two atoms of the same kind is an exceedingly challenging task. Factors like the movement or rotation speed of atoms influence their ability to form chemical bonds, making seemingly identical atoms behave differently. Even when two atoms are essentially the same chemically and exhibit identical reactions, they cannot be deemed completely identical, extending this assertion beyond considerations of electrons to encompass the nucleus of an atom. In the grand cosmic drama, the intricate journey of the first atom's formation unfolds, intricately woven into the fabric of our vast universe. From the monumental event of the Big Bang to the epoch of inflation, the photon epoch, and the formation of stable neutral atoms, the narrative guides us through cosmic evolution. Cosmic phenomena create a unique environment for certain particles to endure, paving the way for the elemental building blocks essential for the formation of atoms. Embarking on the cosmic journey also involves delving into the realm of a quantum theory of gravity during the Planck epoch, an intricate merger of the principles governing gravity and quantum mechanics. This epoch, at an astonishingly minuscule scale of 10⁻⁻43 seconds, unfolds with the conjecture that all fundamental forces coalesce into a singular grand force. The cosmic timeline takes us through the inflationary epoch, the electroweak symmetry breaking, and the quark epoch, marking pivotal junctures in the universe's formative epochs. The epoch of Big Bang nucleosynthesis, BBN, introduces equal numbers of protons and neutrons, setting the stage for the emergence of specific nuclei through various transformations. As the universe expands and cools, a symphony of particle-antiparticle annihilation engenders the emergence of stable particles, laying the groundwork for the formation of atoms. The photon epoch, lasting approximately 380,000 years, unfolds with predominantly ionized nuclei interacting with electrons. The cosmic alchemy required for the formation of stable neutral atoms hinges on the essential interplay between electrons and positively charged nucleons. Recombination heralds the birth of stable neutral atoms, liberating photons from their entanglement. For cosmic spectators, the present-day cosmic microwave background, CMB, captures the moment when the first stable neutral atoms make their cosmic debut, offering crucial revelations about the nascent universe and the intricate genesis of atoms. The exploration delves into the nature of atomic interactions, challenging conventional perceptions. At the microscopic level, atoms and molecules engage in a perpetual dance, and while atoms don't have a solid surface, their interactions are influenced by electromagnetic forces. Quantum mechanics plays a pivotal role, revealing the probabilistic nature of electrons' locations and the intricate dynamics within the microcosm. The inquiry into the question of whether atoms ever truly touch each other leads to a profound contemplation of the fundamental nature of atomic interactions. While there's no physical touch in the conventional sense, atoms are always in contact, engaging in a dance of interaction governed by electromagnetic forces. The exploration extends to the concept of identical atoms within the same element. No two atoms of the same chemical element are usually identical, considering variations in electron states, movement, and rotation. This understanding encompasses not only electrons but also the nucleus, emphasizing that achieving perfect identicality between atoms of the same kind is an exceedingly challenging task. The cosmic journey further explores the intriguing realm of color at the atomic level. While individual atoms don't exhibit colors in bulk reflection, thermal radiation and gas discharge processes create colorful displays. The emission spectra of elements in gas discharge reveal unique color fingerprints, but the concept of color at the atomic level challenges conventional perceptions. Finally, the exploration touches upon the fundamental forces governing atomic behavior, including electromagnetism and the strong nuclear force. The intricate dance of these forces allows atoms to exist and form stable structures despite the repulsive forces predicted by Coulomb's law. The cosmic and microscopic narratives intertwine, revealing the awe-inspiring complexity and beauty of the universe at both the grand and infinitesimally small scales. Electromagnetism, operating at the atomic nuclei scale, is crucial for understanding the binding of protons within the nucleus. The strong nuclear force, distinct from electromagnetism, plays a key role in resisting the electromagnetic push, constituting about 99% of the mass of everyday matter. The intricacies of the strong force involve quarks and gluons within protons and neutrons, where quarks come in up and down varieties and gluons possess color charges, creating a unique interplay. The strong nuclear force acts at short distances, binding nucleons together and preventing stable atomic nuclei from expanding beyond certain limits. The strong force operates in harmony with the electromagnetic force, and understanding its intricacies is fundamental to unraveling the nature of matter. Probing the size of a proton, a fundamental subatomic particle, has undergone significant developments. Contrary to oversimplified notions of a smooth billiard ball, a proton is described as a cloud of quarks held together by gluons, adding complexity to our understanding. Scientists have traditionally used electron-based methods and energy dynamics within atoms to estimate the proton's radius, involving intricate investigations and observations of interactions. A groundbreaking experiment in 2010 challenged existing notions, using muons instead of electrons. Muons, due to their greater mass, spend more time within the proton, making them more sensitive to its size. This departure from traditional methods led to a re-evaluation of proton size, uncovering a 4% smaller value. Subsequent experiments using standard electronic hydrogen, conducted in 2019, aligned with the muonic hydrogen results, providing a more cohesive understanding of proton size. This exploration into proton size has evolved into a dynamic journey, challenging and expanding our understanding of the universe's fundamental building blocks. The convergence of results from different methodologies suggests that previous discrepancies were likely due to measurement errors rather than indicating novel realms in particle physics. Contemplating the seemingly contradictory nature of atoms, where most space is considered empty, involves an analogy of magnified tables and atomic behavior. Despite the significant scale, the nucleus at the atom's center remains minuscule and invisible, and the question arises about the solidity of objects. To unravel this mystery, understanding the intricate behavior of electrons within atoms is essential. The initial understanding of electrons, compared to planetary orbits, is acknowledged as oversimplified, prompting a deeper exploration into their behavior and its implications for the tactile experience of touching objects. In essence, the exploration delves into the forces and dynamics governing subatomic particles, challenging preconceptions and leading to a richer comprehension of the universe's intricacies at both the quantum and macroscopic levels. Electrons don't revolve around the nucleus like planets orbiting the sun. Instead, envision them as a dynamic swarm, much like the swift and unpredictable movements of bees or birds. While tracking individual electron motions within this swarm is practically impossible due to their rapid pace, their collective behavior forms distinct patterns resembling a synchronized dance. This electron dance adheres to specific predetermined patterns governed by Erwin Schrödinger's mathematical equations. These patterns exhibit a spectrum of dynamics, from graceful and gradual, reminiscent of a waltz, to spirited and rapid, akin to a Charleston dance. Each electron strictly adheres to its unique pattern, and the exclusion principle ensures that no two electrons within an atom perform the same step. By picturing electrons as participants in a complex dance, we gain insight into the organized chaos at the atomic level, contributing to the overall understanding of the physical properties defining the solidity of everyday objects. Despite not tiring, electrons transition between dance patterns involving the exchange of energy. Transitioning to a faster dance pattern requires energy input, while moving to a slower pattern results in energy release, often in the form of light. When external energy, in the form of light, interacts with electrons, they absorb some energy, transitioning to a higher, more energetic dance pattern. For a light beam traversing through a material like a table, electrons absorb energy from the light, hindering its progress. After a brief interval, these electrons release the gained energy, potentially as light again. The interplay of absorbed and reflected light, coupled with changes in dance patterns, manifests as reflections and colors, collectively contributing to the perception of the table as a solid object. The question arises, if light doesn't penetrate far into the table, how does the table feel solid to touch? The sensation of solidity when touching an object like a table is intricately tied to the dynamic interactions of electrons within atoms. As you touch the table, the electrons in the atoms of your fingers come into proximity with the electrons in the atoms of the table. When the electrons of one atom approach the nucleus of another atom, their established dance patterns undergo a transformation. This transformation arises because an electron in a lower energy level around one nucleus cannot replicate the same dance around the other nucleus, as that particular slot is already occupied by one of its own electrons. Consequently, the incoming electron must transition into an unoccupied, more energetic role. This shift in dance patterns demands energy, supplied by the force from your probing finger. Pushing two atoms in close proximity necessitates energy, as all their electrons must transition into unoccupied high-energy states. Attempting to bring together all the atoms in the table and those in your finger requires a considerable amount of energy, more than what your muscles can readily provide. The resistance you feel while pushing against the table with your finger results from this energy demand, explaining why and how the table imparts a solid feel to your touch. Diving into the question of why atoms form molecules, it's crucial to recognize that the visible universe primarily consists of fewer than 100 naturally occurring elements. However, the remarkable diversity of chemical substances we observe arises from the fact that atoms seldom exist in isolation. Instead, they avidly engage in chemical bonding, combining with other atoms to form molecules. This propensity for bonding gives rise to an extensive array of chemical combinations and materials, contributing to the myriad phenomena observed in the universe and the intricate structures essential for life, energy sources, consciousness, and various macro-scale processes. The universe avoids monotony because atoms form bonds, resulting in complex chemicals with properties fundamentally distinct from their individual constituent atoms. This fascinating occurrence unfolds due to the pivotal role that energy plays in the intricate process of molecule formation, deeply rooted in the principles of quantum mechanics. In essential chemicals shaping our everyday experiences, such as the air we breathe, molecules take precedence over individual atoms. Oxygen presents itself as O2, featuring two oxygen atoms bound together. Similarly, nitrogen manifests as N2, and water adopts the composition H2O, comprising two hydrogen atoms and one oxygen atom. The prevalent existence of atoms in the form of molecules can be attributed to their innate inclination to assume a state of lowest energy, akin to a marble atop a hill effortlessly rolling down to the bottom. Across the natural world, systems consistently strive to minimize their potential energy, elucidating phenomena like the unidirectional flow of rivers from elevated terrain to lower ground. Energy, a key player in the orchestration of molecular structures, becomes particularly significant when examining the simplest atom, hydrogen, comprising one proton and one electron. Quantum mechanics provides valuable insights into the rationale behind atoms forming molecules as they seek lower energy states. The introduction of a second hydrogen atom brings forth intriguing interactions. As these atoms draw closer, the negatively charged electrons, repelling each other due to their shared charge, are simultaneously influenced by the positive charge emanating from the protons in the neighboring atom, resulting in an attractive force. A delicate equilibrium is established, marked by an optimal distance where protons prefer to reside, allowing for the sharing of electrons while minimizing repulsion. It's crucial to recognize that the attraction between atoms isn't solely dictated by the repulsion within their electron clouds. Rather, a multitude of intricate interactions comes into play, shaping the dynamic landscape of molecular formation. In essence, the dance of electrons and the interplay of charges at the quantum level pave the way for the cohesive existence of atoms as molecules, each striving for a harmonious balance of energy states. The intricate dance of atoms shaping the formation of molecules is intricately governed by the overarching concept of total energy within a system. This all-encompassing energy factor intricately guides the bonding interactions between atoms, orchestrating the emergence of cohesive molecular structures. delving into the exploration of the lowest energy state in a two-atom system, exemplified by the formation of a hydrogen molecule, entails a comprehensive consideration of various elements. The kinetic energy inherent in each atom, intertwined with the potential energy dynamics between protons and electrons, contributes to the system's total energy framework. In the realm of quantum mechanics, these complex energy calculations find encapsulation in the Hamiltonian, a fundamental representation of the system's energy. However, the unraveling of this energy tapestry involves the intricate solving of the time-independent Schrödinger equation, with the Hamiltonian as its guiding force. While this equation poses a formidable challenge to direct resolution, its essence is often graphically portrayed, providing a visual narrative of energy fluctuations. As two atoms draw closer within this graphical representation, a distinctive dip emerges, symbolizing the system's lowest energy state. When the atoms attain an optimal proximity, the optimal state encapsulates a harmonious union where the two atoms, in this coalescent configuration, find themselves in a more contented state at a lower energy level than when existing in isolation. This phenomenon elucidates the natural tendency of hydrogen atoms to synergize, forming molecules of H2, rather than persisting in a solitary state. This electron-sharing pact between atoms, known as a covalent bond, extends its reach to forge similar covalent bonds between a myriad of other atoms. Unraveling the stability secrets of atoms involves an exploration of the electron arrangement within their orbital shells. Encircling the nucleus, particularly stable configurations emerge, providing stability to the resulting molecule. The concept of total energy within the system becomes the guiding force orchestrating the dance of electrons and the interplay of charges. At the quantum level, the intricate dance of atoms shapes the formation of molecules, governed by the overarching principle of achieving a harmonious balance of energy states. In conclusion, the dance of electrons, the interplay of charges, and the pursuit of lower energy states form the foundation for the cohesive existence of atoms as molecules. This intricate molecular dance, intricately governed by quantum mechanics, contributes to the diverse array of substances and materials observed in the universe. From the solidity of everyday objects to the complex structures essential for life, energy, and consciousness, the dynamics of atoms and molecules shape the intricacies of our macroscopic world. Configurations arise when atoms have specific electron counts, such as 2, 10, 18, 36, 54, or 86. These magic numbers correspond to the electron tally of naturally occurring noble gases, which are known for their chemical inertness and reluctance to readily bond with other atoms. The stability and bonding tendencies of atoms weave a captivating narrative intricately entwined with the tapestry of quantum mechanics. Atoms embark on a quest for stability by aiming to achieve a complete valence shell of electrons. This pursuit manifests through either the collaborative endeavor of sharing electrons in covalent bonds or the transformative act of transferring electrons in ionic bonds. The magnetic interplay between the attractive force propelling electron sharing for a full valence shell encounters a delicate equilibrium with the repulsive forces emanating from electron clouds and protons within the atomic nucleus. Exploring the rationale behind the intriguing magical numbers guiding atomic stability unveils a narrative rooted in the realms of quantum mechanics. The Schrödinger equation and the Pauli exclusion principle significantly contribute to deciphering the underlying order. The Pauli exclusion principle asserts that no two fermions, such as electrons, can occupy identical quantum states, necessitating opposite spins for electrons sharing the same orbital. The combination of these principles leads to the identification of specific numerical sequences, known as magical numbers, dictating configurations resulting in the lowest potential energy within chemical systems. Navigating the complexities of multi-atom systems like water, H2O, requires comprehensive calculations. The Morse potential equation, often used as an approximation, proves instrumental in determining bond length conducive to the molecule's lowest potential energy. Quantum mechanics, with its intricate principles and mathematical formulations, emerges as the guiding light illuminating the intricacies of nature's behavior. However, it's crucial to note that while quantum mechanics offers profound insights into the mechanics of the natural world, it doesn't inherently provide a deep understanding of the fundamental why behind the inherent nature of existence. Transitioning to the intriguing realm of neutron stars, a compelling inquiry arises. Is a neutron star akin to a colossal atom? Neutron stars stand out as some of the most extraordinary entities in the universe, resembling colossal atomic nuclei with diameters extending over several kilometers and possessing mind-boggling density and inherent violence. The sheer existence of such a phenomenon prompts the profound question of how something of this nature can possibly exist. The life of a star involves a delicate balance between the relentless force of gravity and the counteracting radiation pressure generated by fusion reactions at its core. As a star's core undergoes successive layering with progressively heavier atomic nuclei accumulating, the fusion journey culminates in the creation of iron. If the core mass exceeds approximately 1.4 times that of the Sun, a catastrophic collapse ensues, leading to the formation of a neutron star. At this critical juncture, the fundamental forces within an atom come into play, working to counteract the gravitational collapse. The effect of the weak force in this hot, dense plasma allows newly formed protons to easily change identity to become neutrons and vice versa. During the freeze-out period, the hadrons choose an identity once and for all, shaping the balance between protons and neutrons. This slight mass difference ultimately results in an imbalance in the number of protons to neutrons in the universe, playing a crucial role in the formation of elemental interactions, chemistry, and biology. Expressing gratitude for the universe's unexplained preference for protons over neutrons, we recognize how a different scenario could have led to a vastly different universe. The absence of antimatter, another mysterious imbalance, becomes embedded in the cosmos during this stage of its evolution. This fortunate asymmetry contributes to the stability and existence of the universe as we know it. As we delve into the possibilities of extraterrestrial civilizations, we explore the potential risks associated with advanced technologies, specifically the use of antimatter as a powerful energy source. The catastrophic consequences of antimatter weaponry, triggered by conflicts and wars on an alien planet, underscore the destructive potential of harnessing antimatter for destructive purposes. In conclusion, the exploration of magic numbers, quantum mechanics, neutron stars, and the absence of antimatter reveals the intricate balance and interplay of fundamental forces that govern the structure and existence of the universe. From the atomic scale to the cosmic level, these phenomena offer insights into the complexity and beauty of the natural world. Proteins. The entire world experiences a profound transformation with repercussions echoing through centuries, illustrating the catastrophic outcomes when antimatter encounters matter. Remarkably, antimatter surrounds us daily. Now, let's embark on a cosmic thought experiment, contemplating what if the entire universe resembled an atom. The observable universe, vast and challenging to comprehend, may, according to certain theories, be relatively insignificant. Current calculations suggest that the unobservable universe could surpass even the immense size of 20 trillion light-years in diameter. Despite its colossal scale, a substantial portion of this cosmic expanse might be devoid of matter, akin to the sparsity observed in the observable universe. Matter, the fundamental building block of everything we know, is composed of countless atoms, too small to be directly observed by our most advanced microscopes. Scientific evidence supports the existence of atoms, composed of subatomic particles like protons, neutrons, electrons, and quarks. Intriguingly, there are theories proposing a grander reality where everything, humans, the entire observable and unobservable universe, resembles an atom in a larger cosmic context. One such concept is the one-electron universe theory, suggesting that our perception of multiple electrons might originate from a single particle moving swiftly back and forth in time, creating the illusion of multiplicity. While this idea lacks robust scientific support, it serves as a thought-provoking starting point for other similar concepts with more scientific backing. A more widely acknowledged variation is rooted in the multiverse theory, positing that every atom, electron, and property of matter in our universe could be equivalent to an atom in a grander cosmic scheme. This notion expands our understanding of the universe's intricacies, inviting us to contemplate the vast possibilities beyond the boundaries of our observable cosmos. The idea of our universe being a mere speck in a broader realm has intrigued the realms of science fiction, envisioning our universe as a tiny entity on a higher plane of existence, or each atom within us potentially harboring entire other realities. Infinity becomes a crucial element, suggesting that no matter how vast our universe appears, the multiverse theory postulates the existence of potentially infinitely larger universes. From the perspective of these hypothetical vast realms, our universe could seem as minuscule as subatomic particles appear to us. When we observe the universe, we witness the intricate dance of minuscule subatomic particles forming progressively larger structures, from celestial bodies to intricate living organisms. This prompts a profound question. Could the universe itself be just a component of something even more grandiose? The merging of the microscopic and macroscopic realms urges us to withhold judgment until we develop a comprehensive theory of everything that seamlessly unifies the principles of quantum and classical physics. According to the prevailing theory on the universe's origin, it began as an infinitely dense singularity before expanding through the monumental event known as the Big Bang. This implies that everything we currently comprehend was once unimaginably small. However, it's crucial to distinguish this initial singularity from an actual atom, as it contained the fundamental components necessary for the formation of atoms. While these concepts may challenge our conventional understanding of reality, they serve as valuable thought experiments, encouraging contemplation of our place in the vast cosmic tapestry. Although they might be mind-bending, they don't diminish the wonder and significance of our existence. One leading contender for a comprehensive theory of everything is string theory, which seeks to unravel the true scale of reality. In this theoretical framework, atoms are not envisioned as spherical objects, but rather as string-like structures that vibrate, giving rise to all interactions in the universe, including the fundamental laws of physics, gravity, and quantum mechanics. However, string theory grapples with challenges, particularly in addressing dark energy, a substantial constituent of the universe that remains a puzzle yet to be fully unraveled. Many string theory models face a significant challenge in elucidating the prevalence of dark energy when compared to observable matter. In recent efforts to reconcile these disparities, researchers from Uppsala University in Sweden have proposed a variation within string theory. This novel perspective suggests that our universe might reside on the periphery of a perpetually expanding bubble, where everything familiar to us constitutes a small segment of a much larger cosmic structure. Within this bubble, and possibly extending beyond its limits, uncharted dimensions could exist, and the infiltration of dark energy from the broader bubble universe offers a potential explanation. If this unconventional portrayal of reality were accurate, it would revolutionize our current scientific understanding, positioning human beings as infinitesimally small components within a vastly intricate and incomprehensible structure. Nevertheless, it's crucial to acknowledge that this concept serves as a thought experiment, a captivating way to contemplate our role in the vast cosmic expanse. Even if our perspective proves limited and our understanding imperfect, the potential insignificance from an alternate viewpoint doesn't necessarily diminish the intrinsic value of our existence. Now, let's ponder a timeless question. What happens to your atoms after you die? Throughout human history, over 100 billion individuals have departed this life. Considering the law of conservation of matter, which posits that matter cannot be created or destroyed, one might wonder about the fate of these countless atoms. Surely, their atoms must still persist in some form, right? Let's explore an intriguing idea that the atoms of your departed loved ones haven't simply vanished, but have become an integral part of you, the world around us, and are presently embarking on a captivating journey across the universe. Delving into this concept allows us to unravel the fascinating ways in which this transformation occurs. The human body is a complex composition consisting of approximately 60% water, 20% fat, 15% proteins, 2% carbohydrates, and 2% salts and minerals, along with 1% other elements like oxygen gases and vitamins. The majority of the molecules within our bodies take the form of water, H2O. When an individual passes away, this water undergoes a transformative process. It either evaporates from the body, entering the atmosphere or seeps into the ground. The speed of this process hinges on various factors, including temperature and environmental conditions. Even if the water remains in liquid form, it eventually becomes a part of Earth's water cycle, transitioning from liquid to vapor or ascending to the clouds, and eventually returning as rainwater. A significant portion of this rainwater finds its way into rivers, lakes, and eventually becomes part of our drinking water. Your body utilizes this water for diverse purposes, such as integrating it into cells, regulating temperature, and sustaining various bodily functions. Some of the rainwater is absorbed by plants, playing a pivotal role in photosynthesis. This chemical reaction involves water, carbon dioxide, and sunlight, producing carbohydrates and oxygen. The oxygen released by plants is then breathed in by you and other living beings to support life. Moreover, the carbohydrates resulting from water and photosynthesis become a crucial part of your diet, as well as the diet of other animals, through the consumption of fruits and vegetables. This intricate cycle demonstrates how the atoms that once constituted your departed loved ones continue to contribute to the vibrant tapestry of life, highlighting the interconnectedness of all living things and the perpetual journey of atoms through various forms and functions. As we explore the intricate journey of atoms and molecules, let's delve into the fascinating realm of metabolism. When you consume carbohydrates from plants, an essential process occurs, the production of substances vital for plant life, namely carbon dioxide and water. This sets in motion a continuous cycle where the very elements you generate contribute to the growth and sustenance of plant life. Now that we've uncovered the fate of water molecules, H2O, in your body, let's unravel the destiny of your soft tissues composed of carbohydrates, fats, and proteins. Proteins, essential tissues in your body, undergo metabolism with the assistance of approximately 100 trillion bacteria residing within you. These bacteria, primarily in your gut throughout your life, are normally kept in check by your body's robust immune system. However, upon death, the immune system ceases to function, providing these bacteria with the opportunity to consume the tissues within your body. In this intriguing process, as these bacteria metabolize your soft tissues, they utilize them for energy and reproduction, gradually transforming molecules into water and carbon dioxide, akin to a gradual burn. Moreover, proteins in your body give rise to other gases like nitrogen oxides and ammonia during this metabolic process. What makes this process even more remarkable is that these gases, especially nitrogen oxides, are potent greenhouse gases, approximately 300 times more potent than carbon dioxide in contributing to the greenhouse effect. This emphasizes the intricate interplay of chemical processes within the body, showcasing how even after death, the elements within our bodies continue to participate in complex cycles with broader implications for the environment. As we delve deeper into the fascinating realm of post-mortem processes, the journey of atoms within our body takes a unique turn. As the initial bacteria continue their metabolic activities and oxygen becomes scarce, a new set of bacteria, known as anaerobic bacteria, seize the opportunity. Unlike their aerobic counterparts, these bacteria don't rely on oxygen for metabolism. Instead, they produce byproducts such as methane, hydrogen sulfide, and ammonia during the metabolization of tissues. These byproducts, notorious for their unpleasant odors, also serve as potent greenhouse gases, gradually dispersing into the atmosphere. When you step outside and detect an unusual scent in the air, there's a chance that you might be inhaling atoms originating from your great-grandmother or others who came before. Additionally, atoms and molecules from your body are released into the underlying soil during decomposition, contributing essential components like nitrogen, phosphorus, potassium, and magnesium. These components act as natural fertilizers for the plants surrounding the burial site, playing a positive role in the local ecosystem. Now, let's shift our focus to the alternative process of cremation. After your body undergoes cremation, the intense heat of the process leads to the conversion of the majority of atoms in your body, hydrogen, carbon, nitrogen, oxygen, and sulfur, into gases. Various gases, including water vapor, carbon dioxide, nitrogen oxides, and sulfur oxides, are released into the atmosphere. A considerable portion of your remains transforms into ash during this process, and intriguingly, the weight of these ashes is roughly equivalent to your birth weight, underscoring the cyclical nature of life. Analyzing the composition of these ashes reveals that the bulk consists of phosphate and calcium, integral to the structure of your bones. Consequently, these atoms predominantly originate from your skeletal framework. These ashes are likely to find their way into the soil, becoming integrated into the structure of plants. In turn, these plants may become a source of nourishment for animals and humans, facilitating the return of the remnants of your existence to human bodies. In a fascinating twist, small fragments of you could end up in the morning cereal or burger of your great-grandchildren, allowing you to persist in contributing to the sustenance of life on our planet. However, it's crucial to note a significant exception. Your body contains trace amounts of radioactive elements. Some of these elements undergo spontaneous fission through radioactive decay, transforming into other elements before entering the biosphere. For example, radioactive potassium may transition into calcium, while minute quantities of thorium and uranium within your body will eventually evolve into lead. Alongside this decay process, certain helium atoms are generated due to the insufficient gravitational force on our planet. Helium tends to escape into space, though a fraction of it may be captured by massive celestial bodies like the Sun and Jupiter. This intricate interplay of elements adds a layer of complexity to the cosmic journey of atoms, highlighting the dynamic processes at play in the broader universe. As we contemplate the cosmic destiny of atoms, a notable portion embarks on an extraordinary journey beyond the confines of our solar system. These atoms, once part of your composition, set forth on an awe-inspiring voyage, drifting amidst the stars and venturing into the vastness of the cosmos. Their trajectory carries them to the farthest reaches of the universe, where they persist in perpetual motion, transcending time itself. A captivating question arises: do atoms last forever? While life on Earth appears constant and predictable, marked by the rhythmic ebb and flow of tides, the daily cycle of the sun, and the unchanging progression of months, the larger cosmic panorama reveals a dynamic tapestry of changes and activities. Each day witnesses the birth and demise of millions of stars, and even our own sun, billions of years in the future, is destined to face a similar fate. As our sun undergoes a transformative process, transitioning into a red giant, Earth will experience rising temperatures, ultimately leading to the extinction of life. A few billion years later, the sun will exhaust its nuclear fusion fuel, initiating its inevitable demise. In this cosmic spectacle, the sun will cast off its outer layers, gradually fading into darkness. The cosmic truth emerges. Nothing in our universe endures eternally, or does it? Enter atoms, the elemental building blocks of matter that form the very fabric of our universe. When we contemplate the end of our individual existence, it's crucial to recognize that our bodies, composed of these enduring atoms, do not simply vanish into nothingness. Instead, they undergo a profound transformation, embarking on an intricate journey that extends beyond our mortal coil. Instead of disappearing, our bodies undergo a transformative process, breaking down into their fundamental components and seamlessly becoming integrated into the ecosystem once again. In simpler terms, the atoms that constituted us persist long after our physical presence has ceased. Now the question arises, how long can atoms endure? Is there a point at which they cease to exist? To unravel this question, we must delve into the inner workings of atoms. Atoms, as you might be aware, comprise protons and neutrons encircled by a cloud of electrons. The stability of an atom is intricately linked to the balance between the number of electrons and protons. Ultimately, the atomic number, which determines the atom's identity, is dictated by the number of protons. For instance, helium, occupying the second position on the periodic table, boasts an atomic number of 2 due to its 2 protons. While the number of neutrons in an atom is typically constant, exceptions exist. In cases where an atom lacks the correct number of neutrons, it may shed a neutron, akin to misplacing a sock in the wash. This imbalance renders the atom unstable, prompting it to emit subatomic particles. Often, this emission involves the release of an electron, ushering in changes within the atom. When dealing with heavy atoms, there's a likelihood that they might spontaneously break down into smaller particles, a phenomenon known as radioactive decay. This process is fundamentally random, making it challenging to predict the precise moment of breakdown or the emission of subatomic particles. Nevertheless, statistical analysis allows us to estimate the average time it takes for half of the atoms in a sample to undergo decay, termed the half-life. Given that atoms possess a finite number of protons and neutrons, they generally emit particles until they reach a state where their half-life is so extensive that they essentially become stable. Take, for instance, bismuth-209, believed to have the longest decay rate. Undergoing alpha decay, its half-life is over 1 billion times longer than the current estimated age of the universe, showcasing the enduring nature of certain atoms. This emphasizes that despite their dynamic nature, certain atoms can persist for unimaginably long periods. In practical terms, bismuth-209 exhibits remarkable longevity to the point where it is often considered nearly eternal. However, the concept of true eternal life for subatomic particles raises intriguing questions about the potential decay of protons. Scientists have proposed hypotheses related to proton decay, a theoretical form of radioactive decay. One such idea, known as the Gori-Glasso model, suggests that protons could undergo a transformation into a positron and a neutral pion. Subsequently, this neutral pion decays into 2 gamma-ray photons. The estimated half-life for protons in this model is an astronomically extended 1.29 * 10 to the power of 34 years, creating a hypothetical pathway towards eternal life for protons. However, it's important to note that as of now, there is no experimental evidence to substantiate the occurrence of proton decay. Despite the absence of conclusive experimental support, ongoing research at some of the world's leading laboratories holds the promise of potentially shedding light on this intriguing aspect of particle physics. Through a combination of luck and rigorous scientific investigation, future insights may emerge, unraveling the mysteries surrounding the potential decay of protons and offering new perspectives on the concept of eternal life at the subatomic level. From stars being born in the sky to tiny particles quietly fading away, the universe shows us a beautiful dance of creation and disappearance. Right in the middle of it all, atoms stick around, changing over a really long time and connecting the past, present, and future. As we think about some atoms possibly living forever and the tricky idea of true eternal life, the universe asks us to think about really tiny things and really big things. Maybe in the dance of tiny particles, we see people trying to figure out what life means and how things last. In this huge dance of the cosmos, our search for understanding is a lot like how atoms keep changing from old thoughts about life to new scientific questions. People are always trying to understand what existence and forever really mean. Atoms, these quiet things that carry stuff around quietly, tell us that everything has a beginning and eventually an end. But even in this pattern of things being made and breaking down, there's something beautiful. There's a kind of connection that ties us to the universe. The atoms in us have seen a lot. Ancient times, stars, and whole galaxies. They've watched the universe's dance that keeps changing. An everlasting dance that goes beyond time and space limits. As we travel through the huge space of the universe and the really small world of atoms, let's appreciate how everything is connected. In the dance of tiny particles, we find similarities with our own short-lived time here, reminding us that, like atoms, we're part of the big story of the universe that unfolds over a very long time. Thanks for watching.